Let's now discuss the time rates of change experience in fluid mechanics. For this, we have created this image where we have a row of particles of different size. Suppose the size of the particle is expressed as a variable eta, del eta by del x, which is positive, constant, it is the value of eta, the size, is changing to the right. Now suppose all these particles are moving with the velocity v. After time delta t, the original row is now located at this configuration. The blue arrow is an observer observing the fluid property. If the blue observer has closed its eyes at the start of the motion and opens its eyes delta t time later, then it will see this picture. It will record that the size of the particle, the property eta, has decreased. What has happened? What has happened is this. Now, a particle which was v delta t distance behind the original particle at the diamond probe has occupied this location. The whole row has moved a distance v delta t to the right. So, if the size of the particle was not changing, then originally it recorded the particle which was at this location x, but delta t times later it was recording the size of the particle which originally was at minus v delta t behind the current location. So, change in property observed is delta eta is equal to del eta by del x into minus v delta t. This change has been recorded purely because of the motion of the particle. So, this change can be called the convective change following the lead from heat transfer, where the convective heat transfer is because of the motion of the fluid. So, this change in property eta is solely because of the motion of the fluid particles, and of course because of the gradient of the property eta in space. Because if delta eta by delta x was 0, then all particles were the same size. No motion would show any change in the value eta at the location of the probe. Now, if in addition during this time delta t, the size of each particle increases, if the size of each particle increases, then the change in eta observed by this observer would be the original convective change delta eta by delta x into minus v delta t plus the rate at which the size of the particle grows. We denote it by capital D eta by delta, capital dt. Capital D eta by capital dt is the material rate of change of eta with time of the actual particle, the growth of the size of each particle. We call this the material rate of change. And so the total change in time delta t would be capital D eta by capital D t times delta t. So the total change observed by this observer would be the convective change plus this material change. And the rate of change with time is given by the equation at the bottom of the slide. Delta eta by delta t is equal to minus v delta eta by delta x plus d eta by delta t. Del eta by del t on the left is the observed rate of change. We call it the local rate of change. Locally observed rate of change by a stationary observer. A field description, an Euler-Arian description. And this consists of two changes. One is the rate of change minus v delta eta by delta x, which is the convective rate of change, plus capital D eta by capital dt, which is the material rate of change. The local rate of change is made up of two things: a convective rate of change and a material rate of change. So repeat, the local rate of change d eta by dt is made up of two changes. One, convective rate of change, and the other, the material rate of change. This equation is conventionally expressed in this form. D eta by dt, the material rate of change, is equal to the local rate of change plus the convective rate of change. This cartoon explains this quite clearly. There are two scientists, Mr. Euler, who is stationary, and he reports a local rate of change at 2 degrees per hour, rising at 2 degrees per hour temperature. Mr. Lagrange, of the material property fame, is floating down the river on a boat, so he's measuring the material rate of change. And he says the temperature is dropping at 1 degrees per hour. What's happening? That there is a spatial gradient. There's a convective rate of change that defines this difference. Let's take an example. On a given day, temperature at Dehradun is 15 degrees Celsius at sunrise, and at the same time, the temperature at Jhansi, almost exactly south of Dehradun, is 25 degrees centigrade. Jhansi is about 500 kilometers from Dehradun. There's a 30 kilometer per hour wind that blows due south, and the air heats up at the rate of 1 degree Celsius per hour. What is the rate of rise of temperature at Jhansi? To understand this, let us understand what does air heats up at 1 degree Celsius per hour mean. Is this the local rate of change or the material rate of change? It clearly is the material rate of change. Each individual particle of air is heating up at the rate of 1 degree Celsius per hour. There is a spatial gradient of temperature. Temperature rises from 15 degrees Celsius to 25 degrees Celsius over a distance of 500 kilometers. So del T by delta X is 25 minus 15, that is 10 degrees Celsius divided by 500 kilometers. The local rate of change at Jhansi, del T by del T, is dt by dt minus V dot delta T by delta X. Material rate plus the convective rate. V dot dt by delta X is equal to 30, velocity is 30 kilometers per hour, into 10 by 500 degrees Celsius per hour. So the local rate of change is 1 minus 0.6 or 0.4 degrees Celsius per hour. So even though each particle of air is heating up at the rate of 1 degree Celsius per hour, the local rate of change felt by the resident of Jhansi is only 0.4 degrees Celsius per hour, because the cooler air is moving in from Dehradun. This is from the property eta that we wrote, this relation. For vector form, we can write this equation as delta eta by delta d eta by dt is equal to delta eta by delta t plus vector v dot, the scalar dot product, time gradient of eta. If eta is taken as the velocity, then dv, d velocity by dt, is acceleration. dv by dt is del v by del t plus v dot del v. This is known as Euler acceleration formula. The term on the left gives you the actual acceleration of a particle. This is a material description, a Lagrange description. The first term on the right is the local rate of change of velocity, and v dot del v is the convective rate of change of velocity, or the convective acceleration. The material acceleration is local acceleration plus the convective acceleration. Those familiar with simple vector operations would recognize that v dot del v consists of three components, I, j and k in the 3 direction. In the I direction, the component is Vx, delta Vx by delta x, plus Vy, delta Vx by delta y, plus Vz, delta Vz by delta z. Similarly, in the y direction and the z direction. We do a simple example. Let the velocity field be a into x minus yj. The velocity component in the I direction, the x direction, is ax, and in the y direction is minus ay. If we plot this velocity at a few points, we get a picture like this. Along the x-axis, where y is equal to 0, the velocity is axi. So velocity is horizontal and it is increasing as x increases. Along the y direction, where x is 0, the velocity is minus ay. So velocity decreases toward the origin and is directed towards the origin. At other location, the velocity vectors are as shown. Now let's determine the acceleration. Acceleration of particles which are at location x and y. Ax, the component by the Euler acceleration formula, was Ax, the x component acceleration, is delta Vx by delta t, the local rate of change, plus the convective rate of change. And if I evaluate each of this term, I get Ax as a square x. There is no Vz component. There is no component normal to the plane of paper. X-axis, similarly, a y is evaluated by differentiating this with respect to t, x and y, and we get a square y. So the acceleration vector is a square xi plus yj. This is the acceleration of the particle which would be at that in the location xy at a given time t. Note that the acceleration is independent of time. The velocity was independent of time. So acceleration is also independent of time. If the velocity is independent of time, why is there an acceleration? Because acceleration is only rate of change of velocity. No, this is velocity field. This is Eulerian description. So even if the velocity at a given point does not change with time, the particle at that point may be undergoing acceleration, because when it moves to the next point where the velocity is higher, that means it has undergone an acceleration. And if I plot this acceleration field, the acceleration field looks like this. These are the acceleration vectors at all times. Let's go to classification of flow fields. We have a one-dimensional flow field we call, when the velocity description Vx is a function of only one space variable. In this channel made of two plates, one of the plates may be moving, there is only x component of velocity Vx, which is a function of y only, so it's called a one-dimensional velocity, one-dimensional field. Similarly, flow through a pipe. We have seen before that flow through a pipe at laminar regime has a velocity field which is parabolic, and it is a function only of r. Vz along the axis is a function of r. This is one-dimensional. If the channel was slowly tapering, very slowly tapering, the field is no longer one-dimensional, but the variations with x direction are slow, and so it can be treated as a quasi one-dimensional. Similarly, we have a name, steady flow. Steady flow is that flow field where the properties do not change with time. So at location x1, the velocity is constant with the time, and well, at any other location x2, the velocity is constant at the higher value for all times. This flow is termed steady flow. So in steady flow, the local gradient is zero. If we're using the property velocity, then del V by del T is zero. The local time rate of change of velocity is zero. But it does not mean that the acceleration is zero, as has been established earlier. In this flow from a large reservoir through a small bored tube of long length, the level of the fluid in the reservoir would change very slowly, so that the velocity of the flow or the flow rate through the tube of area A is going to vary very slowly. And so at a given time, this can be treated as a steady flow. Such flows where the variations are very slow are called quasi-steady flow. We would have occasion later to amplify this assumption. A uniform flow is a flow in which the properties are constant at all x's and y's. That is, everywhere, all properties have the same value. In some cases, we can convert an unsteady flow to a steady flow simply by change of frame. There is a body that is moving towards the left with a constant velocity. Let's consider a point A at a location x naught, y naught and record the change in velocity. Originally, the velocity there would be 0, but as the body moves towards A, the velocity increases, and as the body moves past A, the velocity decreases back to 0 again. So the velocity at A would appear something like this. In this video, which is a famous video from 1933, recorded by the great German aerodynamicist Ludwig Prandtl, we show a body moving in a fluid and the flow is unsteady. We can make this flow steady by changing the frame of reference. Now we attach the frame to the body. Here, the point B is in the frame x naught prime, y naught prime. The body is stationary in this frame. The fluid moves past this from left to right as the velocity v. Then the velocity at point B would always be same, invariant with time. The value would be depending upon the location of B relative to the body. If it is closer to the body, if it is at the nose of the body, the fluid at the nose is always at rest. But far away, the velocity is equal to v, the speed of the body. This is shown in this video again by Ludwig Prandtl. The flow is now steady. Thank you very much.